Okay, in this section we're going to talk about the multiplication rule. We've already talked about the OR rule or the addition rule. Whenever you have a probability statement that has the word OR in it, you should think of addition. And the word AND is for multiplication. The proverb for this section, better is a little with righteousness than great revenues with injustice. Wealth is not the aim of the game, in other words. Many times people try to get wealth and think then my life would be easier, and that is not the case at all. There are so many stories where people try to get rich fast in very bad ways and obviously get caught. So please be careful about how probability and games and everything else plays into you trying to get rich really fast. That doesn't work out. Wealth is not the aim of the game. So let's talk about this word AND. Multiplication rule. Probability of A and B implies that the event A occurs in the first trial and event B occurs in the second trial. Usually the word AND is associated with sequential events. The formal rule is that if the two events are independent, we'll talk about that word here in just a little bit. If they're independent, then you just multiply the two probabilities. Probability of A times the probability of B. And the association there is with replacement. So if you replace, for instance, a marble back in the urn, you start out with the same amount of marbles, and therefore the probability of one does not determine or change the probability of the other event happening. But if you do not replace, then the probability of choosing a new marble from the same urn without replacement is a different probability, and therefore we have a different formula for it. Probability of A and B is equal to probability of A times the probability of B given A has occurred. Right? That vertical bar right there is red, given B, given that A has occurred. And this is an example of dependent probability. We'll talk about this a little bit more in detail. Now, independent events, A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Really quick example, let A be the event that there will be rain today. Let B be the event that you win the lottery, right? The probability of rain and the probability of you winning a lottery are not dependent on each other. One doesn't influence the other. Dependent events, on the other hand, if A and B are not independent, they are said to be dependent. Here's a really quick example of that. Let A be the event that your car starts in the morning. Let B be the event that you get to stats class on time. Right? One actually does have a influence on the other, and therefore the probabilities would be different, or a different way of calculating them. So let's actually do a really quick example here about how to use the AND. Here's an example where it reads here, a multiple choice quiz has two questions. The first is a true-false question, and the other is a multiple choice question with 5 options. Okay, so you want to know then, if a person did not study and was to randomly choose one of the options for each question, don't do that, please study, what is the probability that they would answer both questions correctly? So I want a correct answer on the first and the correct answer on the second. Granted that, think about this, there's a true-false question, so a 50-50 chance of getting the first one right. And then there is there's 5 options in the second exercise. That means, right, 1/5 chance of getting the other one. And I want one and the other to be true. I want both to be true. And so what we could do is set up a tree diagram. It's very, very helpful to set up a tree diagram. The very first event here would be answering the true-false question. So you choose one or the other. The probability is, right, there's 2 options. One out of the 2 is going to be the correct answer. And then there is a multiple choice question that has 5 options, and one of those is true. So suppose that the correct 2 answers are if you answer true on the first and C on the second exercise. So TC would be the correct one. Well, how many total options do we have here? Well, we could have answered true on the first one and one of A, B, C, D, or E on the first one, on the second exercise, excuse me. And then we could have also answered false on the first exercise and A, B, C, D, E on the second exercise. That leaves us with a total of 10 options. Therefore, if we say that only one combination gives you correct answers on first and second exercise, then we have to multiply them. 1/2 times 1/5, or 1 out of the total 10, gets us the probability of getting the first and the second exercise correct. Okay, hopefully that makes sense about why we would multiply. Hopefully that's more intuition for you. So for both of them to be correct, you get 1/10 is the probability, and the multiplication rule applies. 1/2 times 1/5. Notice that this is an example of independent events, right? Saying true or false in the first has no influence on choosing A, B, C, D, E on the second exercise. So this is an example of independent events. Now let's move on to some more definitions and also talk about dependent. What if we choose 2 marbles from an urn with 3 red marbles and 3 white marbles? And so the dependent case would be choose the first marble and then do not replace it, then choose the second marble. Note what will happen when we do that. Well, if we remove 1 marble, then the total number of marbles in the urn has changed, and so the probability of the second marble being chosen will be different. It will be different than if it was when we don't replace it, right? And that's the independent case. Choose the first marble, replace it, then choose the second marble. And that would be the independent case, where you have the total amount of marbles being the same in the first and then the second case. The notation, I already said this, but just a separate slide. It says here P of B, given A has occurred. Probability of B occurs given that A has occurred. And again, remember that if they're independent, then all this is A goes away. So what if A happened? If A and B events are independent, then this A would just go away and you just have probability of B. I'll talk about that a little bit more here in the future slide. So probability of B given A represents the probability of event B occurring after it is assumed that event A has already occurred. And that's how it's read B given that A has occurred, or B given A. So let's do some exercises here. Suppose that you do have an urn with 3 red marbles and 4 white marbles, and the event A here is going to be choose a red marble, and event B is going to be choose a white marble. So what's the probability of choosing a red marble? Well, there's a total of how many? 7, right, marbles. 7 marbles. And then how many are red? 3 of them. So you'd have 3 out of 7 for the first probability. What's the probability of choosing a white? Total is 7, right? So 4 out of 7 would be the next one. And then what if you have 2 that you're going to choose? So find the probability if 2 are chosen. Choosing a white on the second trial and the red marble on the first. So you're going to choose A and B. Probability of A happening and B happening. And then we have to break this down into 2 cases, right? Are we replacing the first marble that we choose, the red marble, or are we not replacing the red marble? That's the dependent case. And so if we take a look at those 2 cases, A and B, in the first case, we have a total of 7 marbles, and so choosing a red would mean 3 out of 7. We want this to happen, the red to be chosen. And what's the probability of choosing a white marble? 4 out of 7. Now notice, the reason that the denominators are both the same is because we replace the first marble. The red marble goes back into the urn, and therefore there's a total of 7 marbles, 4 of which are white, right? And so that gives us a 24.5% chance. Now, assume that the first marble is not replaced. What's the probability of choosing a red marble? There are 3 red marbles out of 7 in the urn. Okay. Now that we don't replace the red one, there are still 4 white ones in the urn, but now a total is decreased by 1 because you've removed that one red one, right? So 4 out of 6. There is now, if you think about it this way, a higher probability of choosing a white marble than there previously was, right? Previously, when we replaced the red marble, now the red marble is kind of getting in the way of us choosing a white marble. But now there are 1 fewer. There are only 2 red marbles and 4, think about this, 4 white marbles, 2 red marbles, and 4 white marbles out of the total 6. So when we multiply that, there's a higher chance of getting a red than a white if we do not replace the red marble. And so you get 28.5% chance. So again, a different way of thinking about it is when you take out a red, there's more chances now that you would get a white marble. That is why this probability at 28.5% is higher than 24.5%. Hopefully that builds some intuition for you about what replacement and non-replacement mean, and again how they're tied into classifying events independent versus dependent. The formal multiplication rule, if probability of A and B is what you want to find, then probability of A times probability of B given A is what you need to calculate. If A and B are independent events, then, as I've mentioned before, probability of B given A is really the same thing as probability of B, right? So think about this. Probability of A times probability of B given A. Well, if it doesn't matter whether A occurs or not, we can just cross that out. And we'll have probability of A times just probability of B, and that's it. Okay? So if the two events are independent, then you have a more simplified formula. And here's where we're going to stop and think about what is the difference actually between independent events and mutually exclusive events. Okay? Independent events and mutually exclusive. We used mutually exclusive, that terminology, when we dealt with the OR statements in the previous section, when we looked at the addition rule, right? And now we've introduced the independent and dependent terminology. What's the difference between the two? Well, the difference, here are some examples, and then I'm actually going to make a list for you guys. So mutually exclusive events cannot happen at the same time, right? There's no overlap. For example, when tossing a coin, you cannot get both heads and tails. And events are independent if the occurrence of one event does not influence the occurrence of the other, the probability of the other event that should happen. So one is talking about there's no overlap, and there can't be if it's mutually exclusive. And if they're independent, then there is no influence of one probability on the next event happening. So you think about it, usually we use multiplication and the words independent and dependent when they are sequential events, one after the other, right? Or one and the other happening. Whereas we use mutually exclusive, that terminology, we want to say one or the other happening. Okay? And there's no overlap if they're mutually exclusive, and if they're not mutually exclusive, then there is overlap. So let me share you guys just a little bit more. Here we go. So we had these two words. So we had the word or. If you see that word in the probability exercise, then you should associate this with the addition rule, right? And there were two cases. We had mutually exclusive events, and for the mutually exclusive events, when there's no overlap, we had that probability of A or B is equal to probability of A plus probability of B. And that's it, because there is nothing in the intersection. The intersection is equal to 0. Whereas if they're not mutually exclusive, then you had probability of A or B is equal to probability of A plus probability of B minus one copy of their intersection, A and B, right? So that's with the word or. Notice, analogous, we have the same thing with the word and, but with the word and, we want one and the other to happen. We use multiplication, times. And just like in the word or, we have, with the word or, we have mutually exclusive and not mutually exclusive. With the word and, we have independent. And the formula for that would be probability of A and B happening is equal to probability of A times probability of B. That's it. Right? It doesn't matter whether A happened or not. Probability of B is probability of B. And then we also have the dependent case where we have probability of A and B is equal to probability of A, and then now A is influencing, the event A is influencing whether B, or what the probability is of having B occur. So now we have times probability of B given that A has occurred, like that. That's the formula for the dependent case. Okay, hopefully that summary of section 4.3 and section 4.4 about the addition rule and multiplication rule is putting things into perspective for you. Let me go back to my slides and show you one more before we go into a different video looking at some more examples. So here again, how do I apply the multiplication rule? If I have probability of A and B happening, multiplication rule says you need to ask yourself, are A and B independent? If they are independent, then you just multiply the two probabilities. If they're not independent, then you need to find what probability of B given that A has occurred and multiply that by probability of A. Okay, so hopefully this helps. Now in the next video, let's try some more application exercises and finding the probability using multiplication.